Hello, my name is Saurabh Kadekodi, and I'm a postdoc at Google Research. And I'm here to give a joint preview session on storage systems for the storage systems related papers being presented at OSDI 2021 and ATC 2021. I'll start by giving a high level overview of storage systems in general. So the objective, the 10,000 foot view of storage systems is efficient storage and retrieval of data. Now, the very popular storage system classes that we interact with regularly are file systems and databases. And in this talk, I'm going to be focusing on the file systems. Now, file systems, as the name suggests, primarily deals with the storage and retrieval of files. There are two main classes of file systems that we interact with regularly. One is the local file system, which is the data that is stored, the files that are stored locally on either your computer or your server or your phone, your tablet, etc. Commonly known popular local file systems are ext4, btrfs, ntfs, etc. And the other class of file systems are the distributed file systems, where data is generally stored on multiple devices and most often on multiple servers, each of which has multiple devices. And this data typically resides in the cloud or in a data center, a storage cluster, and so on. The popular distributed file systems are the Google file system, Lustre, HDFS, etc. Next, I'm going to be talking about the research challenges in both local and distributed file systems before going on to talk about the different papers that are going to be presented in both these conferences this year. So let's look at the research challenges in local file systems. I want to make a note that the research challenges I'm going to talk about are merely a subset of the research challenges that exist. These are the most common ones and the ones that are more popular. Of course, there are other research challenges that also exist, and you must not take this as the superset of all the research challenges that file systems pose. The first is metadata management. So file systems have a lot of metadata associated with them in terms of the directory entries, the file permissions, where the file data blocks are on the storage media, and so on. And there are efficient indexing structures that are constructed in order to help in finding the data of a file, finding the free space to allocate data for a new file, etc. The management of all such metadata, given that there are tens of thousands or even millions of files in your local file system, poses an interesting research challenge. The next is data management. Data management deals with the storage and retrieval of the actual data of the file. This involves designing a favorable on-disk layout based on the type of storage media that you are considering. It may be hard drives, solid-state drives, or non-volatile memory, and so on. The next is crash consistency. So systems crash often, and when you store data on persistent storage media using something like a file system, you want to be able to get that data back if there's a crash or even across reboots. And the crash consistency mechanism of a file system ensures the correct retrieval of data in events of crashes or reboots. Garbage collection is the challenge that deals with reclaiming dead space, which is often created because of deletions. And you want to be able to reclaim the space so that you have enough space to write new data. The file system device interface. So this research challenge is about designing the right API, which has enough flexibility such that the host file system in the operating system in the kernel can interact with the device efficiently to increase device utilization, to reduce the redundant work, and so on. Finally, there is a division of labor, which is negotiating between the host and the device about where a particular task should take place. What is the right place to do that task, and which entity should be doing that task such that it is performed more efficiently. Now, the research challenges in distributed file systems are all of the research challenges that we see in local file systems, because most distributed file systems are essentially a collection of nodes, each of which has a local file system. But in addition to those challenges, there are several other challenges that distributed file systems also have. For example, fault tolerance. Now, when you have multiple devices and nodes and large data centers or storage clusters, failures are common. Along with failures, you also have the events of decommissioning of devices or nodes. And you also have incoming devices and nodes. And the primary responsibility of a storage system is to not lose data. So to maintain redundant copies of data such that you can have fault tolerance in the events of failed devices or servers is the research challenge of fault tolerance in distributed file systems. There is also metadata management, which is an additional layer of metadata management where you need to worry about where the different redundant copies lie, how many copies there are, and so on and so forth. So metadata management in distributed file systems has its own place along with the local file system. We also have to worry about load balancing. For example, if all your data is funneled to a small fraction of devices or servers, those devices or servers can get hotspotted, and they can lead to large tail latencies or generally large latencies, and that might not be acceptable in efficiently running a distributed file system. So the load must be evenly balanced such that the reads and writes take place in a fairly even manner across all the participating nodes and devices. Finally, we have concurrency and scalability, because distributed file systems by their nature have to be able to scale when more and more devices and nodes are added. And so scalability and concurrency is a core component of distributed file systems. Now, I've gone through very fast in introducing the different research challenges in the interest of time. And I spoke about these particular challenges because what I'm going to do now is talk about each paper in the storage area. And I've made tags out of these research challenges. And for each paper, you'll see a bunch of tags associated with that particular paper, along with a banner talking about when that paper is going to be presented. And for each paper, I'm going to be talking about the paper's motivation, their approach, and the result. It's one slide per paper, and I'm going to go through it quickly to give you a preview of the papers of storage systems. The first is ZNS, avoiding the block interface tax for flash-based SSDs. This paper talks about the file system device interface for new hardware such as SSDs or shingled magnetic recording, SMR devices. These devices are append-only devices. And unfortunately, the block layer that exists today is a random write-friendly block layer, an interface which is not very suited for these append-only devices. And so this paper talks about how the block interface is unfit for these newer technologies. This results in these SMR and SSDs having very complex frameworks that have to do a lot of internal I/O and have a high degree of over-provisioning, which makes those devices costly in order to achieve performance and yet be a drop-in replacement for random write-friendly devices such as traditional hard drives. This increases the cost per usable gigabyte, which is called the block interface tax by these authors. And these block interface tax is only projected to get worse as the devices increase with performance and speed going ahead. So the approach of the authors of this paper is to exploit the zoned namespace standard, which is a new standard, which is friendly for append-only devices, where ranges of consecutive blocks on disk are marked as zones, and those zones can be written only in an append-only fashion. While the append-only write rule is enforced by the device, all the other maintenance like garbage collection, etc., is left to the host file system, allowing it higher flexibility in order to perform those tasks. The result is that there is higher flexibility, higher throughput, and lower cost per usable GB, while completely avoiding the block interface tax. The next paper that I'm going to talk about, interestingly, is also about ZNS. ZNS Plus, Advanced Zone Namespace Interface for supporting in-storage zone compaction. Now, we saw the advantage of ZNS, and this paper goes on to say that while ZNS provides a lot of flexibility to the host, maybe that flexibility is too much. In a sense, if we push too much operations to the host file system can get overwhelmed with the amount of work it has to do. Moreover, it is not completely well suited to do certain tasks such as heavy data copying, which is done more efficiently at the device level than by passing the data from the host to the device, where the copying overheads are very high. So the approach of these authors is to offload the data copying operations to the device and let the device take care of that. Along with that, they also relax the strict append-only nature by having sparse sequential writing zones, like subzones within each zone, which helps in performing efficient garbage collection. And they also have identified rules that can be implemented in the device, where the data copy operation, once offloaded to the device can choose from multiple different potential places to put the data and have a cost metric associated with them to store the data wherever the cost is lesser. This results in higher throughput observed by leveraging the device support due to reduced, more efficient I/O by not having the host involved in all activities. The next is optimizing storage performance with calibrated interrupts. Now, whenever you issue an I/O request to a device, the device responds with an acknowledgement via issuing an interrupt. Now, there are competing goals where the latency observed is lower if the device instantly responds or instantly issues the interrupt, whereas the throughput increases if the device waits for a bit, processes a bunch of I/O operations that are close in time, and issues one interrupt encompassing all those operations instead of an interrupt per operation. Now, to navigate through these competing goals, people have developed adaptive heuristics of whether it is better to fire an interrupt instantly or wait. But the authors of this paper argue that today's adaptive heuristic frameworks are not intelligent enough. Rather, they don't have the knowledge of which apps are latent, which operations are latency sensitive. And the problem with that is, if by mistake it misidentifies a latency sensitive operations as one that can wait for batching interrupts, it may cause large latency spikes, which might be unacceptable. In this work, the authors develop a hint mechanism by changing the device interface slightly and passing more bits to the device, telling the device about which operations are latency sensitive and which are not. This allows the device to calibrate its interrupt scheduling mechanism and allow the latency sensitive operations to get their interrupts quicker. Only 2 bits need to be added to the interface to make this change happen. So a tiny change in the application to pass those 2 bits and the device which supports this calibrated or interrupt framework shows an improvement of about 40% in throughput and a latency reduction by almost 86% in a macro benchmark such as RocksDB. A modernizing file system through in-storage indexing. Now, today, similar to the argument in ZNS, what happens is a lot of the file system responsibilities of indexing, finding out where the data blocks lie, etc., lie with the host file system. And the lower level device has to do the job of mapping the logical blocks that are exposed to the file system to the physical entities where the data is actually stored, the physical flash cells. Now, this paper argues that this interface is inflexible, and again, that it puts a lot of responsibility on the host file system. Furthermore, as the file system ages, the device undergoes a lot of fragmentation because the device is not consulted or does not play an intelligent role in deciding where to place devices, because all of that is done by the host file system. So the approach taken by these researchers is to propose a better division of labor by better device management, resulting in lesser I/O and I/O which is more friendly to the nature of the hardware, in this case SSDs. So what they suggest is having a key value interface rather than a block interface with the device. And in fact, they suggest embedding a key value store inside the device, along with pushing other responsibilities such as the crash consistency and the file directory indexing logic inside the device itself. Having a simple key value interface and pushing more responsibilities to the device by having the key value store be a log structured merge tree, which is friendlier for SSDs, shows a lot of throughput improvement in their revised interface. So this allows for simple file system device interface and lower I/O amplification. Re-architecting Linux storage stack for microsecond latency and high throughput. Today's Linux storage stack cannot service both low latency and high throughput applications together. It can either provide low latency or high throughput, but fails to provide both. Today, there are in multi-tenant deployments, many a times you see low latency and high throughput apps contending for the same resources, the same file system, the same cores, and so on. And despite there being multiple IO queues in the block layer in the kernel, low latency and high throughput cannot be achieved simultaneously. The key insight by these authors is that the per core IO queues combined with the multi-queue storage layer and the network hardware makes the Linux storage stack resemble the architecture of network switches. And now, these authors borrow the classical techniques of queuing and priority scheduling from networking literature and apply them to the Linux storage stack. And they see significant improvements by doing that. So they can now perform tens of latency sensitive applications that can run alongside throughput bound applications. And all of this can happen while the latency sensitive applications still provide microsecond latencies. LODIC, logical distributed counting for scalable file access. Now, reference counting is a mechanism used to prevent entities in the kernel like page frames, nodes, or file descriptors from preemptively being garbage collected. Now, millions of counters are not uncommon in today's kernels. There exist distributed counting mechanisms which are at a per core level, which help alleviate the problem of these millions of counters and the bottlenecks resulting from that. But these per core counters suffer from excessive memory pressure and query latencies. The key insight provided by the authors of this paper is that a per process counter is much more effective than a per core counter. This allows a per process counters allows for counters to be present only in processes that actually share the entity as against all the cores by default. This also helps in capturing the skew in popularity. So in the real world, there is a non-uniform distribution of popularity where there are a few entities which are much more popular compared to many of the others, which typically has a Zipf-ian distribution. And so the degree of sharing is captured much more nicely and effectively by per process counters. So LODIC allows up to 65x increase in throughput of read shared file blocks and a 24% increase in macro benchmarks such as the Nginx web server. Z-journal, scalable per core journaling. Journaling is the one of the most common crash consistency mechanisms of local file systems. Journals typically have been a performance bottleneck in many file systems, which is only getting worse with modern hardware such as SSDs and NVMs. Now, per core journals exist, but they suffer from complex journal coherence mechanisms and complex write ordering protocols, which also have their own bottlenecks. And the approach of Z journaling is to still have per core journaling, but overcome the journal coherence mechanisms via smarter techniques. So Z-journal introduces an order preserving write graph, essentially a directed graph that has the ordering captured by having nodes and edges with a direction associated with the time at which the writes had occurred. And each per core journal maintains IDs of ongoing transactions of all the other per core journals. And so without depending on them, by simply noting down the IDs and having a dependency graph of which transaction happened before which other transaction, the Z journal can recover correctly while not depending on the per core journals in the common case of writing to the journal. Moreover, the Z journal can replace existing journaling mechanisms like JBD2 as a drop-in replacement. So file systems that use the JBD2 journal today can directly use the Z journal without any code change. So journal bottleneck workloads as a result of Z journal can see an improvement of up to 4,000%. MapperX, adaptive metadata maintenance for fast crash recovery of DM cache-based hybrid storage devices. DM cache or device mapper cache maps SSDs and HDDs onto higher level virtual block devices. It allows for SSDs to act as persistent caches for HDDs and absorb a bulk of the throughput workload because they're fast and eventually drain to HDDs. To ensure high performance, the DM cache asynchronously persists the dirty bits of the SSDs. So whichever data has been dirtied in the SSD, the bits responsible for marking which data is dirty is persisted lazily. Because of this, when a crash occurs, there is no way of telling which data is stale and which is not, because a bulk of the dirty bits have not yet been written to the device. As a result, all the data has to be marked dirty and reloaded in the case of a crash. What MapperX does is have a smarter data structure, which is cheap enough such that it can store the dirty bits synchronously and prevent the requirement to have to reload all the data when you come back from a crash. This data structure is called the adaptive bit tree, and it's also space efficient because it uses a single bit to represent a contiguous range of blocks and the dirtiness of those blocks. And as a result, with minimal persistence overhead, MapperX can achieve orders of magnitude reduction in the recovery times of DM cache once it crashes. MAX, a multi-core accelerated file system for flash storage. Modern SSDs are heavily parallel, but file systems do not scale to the parallelism provided by these underlying devices. The primary cause of contention identified by the authors is lock contention because of unscalable data structures. The file system and the block layer, therefore, have to use the different cores efficiently in order to keep up with the device parallelism. The approach taken by MAX is to reduce cache coherence by having per core locks and counters. Moreover, they also have an abstraction called file cell, which repacks data and metadata in sort of a blob and allows more than one indexing structures to find where the data is. And so the pressure on the global data structures is reduced. Furthermore, allocation can be divided into multiple independent regions and can happen parallelly, along with the data structures required for maintaining the space of those allocations being independent from each other. By doing this, MAX achieves an order of magnitude higher throughput and significantly higher device utilization through high parallelism. XFUSE, an infrastructure for running file system services in user space. When user space file systems are built, they have to communicate with the kernel, often by doing message passing between the user space and the kernel space, causing user space file systems to traditionally be much slower than their in-kernel counterparts. Furthermore, they also suffer from reliability, availability, and security, which is RAS concerns. As the devices get faster, the RAS and performance problems of user space file systems become worse. The idea of XFUSE is to carefully analyze the path and understand where the reliability, availability, and security concerns exist in Fuse and solve them one by one. An example of the techniques they use is to have lower latency by employing busy waits instead of signals, where you keep polling for the operation to happen rather than sleep and wait for a signal to wake you up. Another example is parallelism at the user level by having multiple daemon threads that communicate with the in-kernel modules in parallel. Thus, XFUSE enables user space file systems to have very low latency of the order of a few microseconds and throughput that exceeds 8 gigabytes per second, competing with the fast storage devices available today. Boosting full node repair in Erasure-Coded storage. So erasure coding is like replication, which essentially is a redundancy mechanism to provide fault tolerance in distributed storage systems. Now, erasure coding has a repair cost associated when a crash occurs, which requires reading the other available data in order to reconstruct the failed data. Existing erasure coding repair optimizations are not uh, optimized for full node or full server failures, but are in fact optimized for a stripe by stripe failure, where a stripe is a collection of chunks. As a result, when full node failures occur, there are hotspots observed in the cluster because a lot of the repair gets concentrated on a few sets of servers that have the available data to reconstruct from. And this disallows the cluster to utilize the full duplex bandwidth, which is upload and download, resulting in unbalanced repair solutions. Moreover, today's erasure coding repair mechanisms cannot incorporate different priorities of repair, uh, depending on which kinds of stripes need to be repaired before which other, if they might have deployed different redundancy schemes. So this paper talks about designing a scheduling framework that can optimize for full node recovery. And they do that by having a repair directed acyclic graph, an RDAG, to capture the data routing and chunk dependencies and spread out the repair to multiple nodes and utilizing higher network bandwidth and more efficient transfers. This significantly improves the full node repair times in cluster storage systems. This is the summary of all the papers regarding the storage area, and I highly encourage you to go to all of these talks, and the details of those talks will be in those presentations. Thank you.